Hi everyone. We have been talking about analysis of trusses using the method of joints, and I'm pretty sure everybody agrees that it's a really boring, time-consuming method, going all over every joint and doing all those calculations. It is. So today we're going to talk about a way of taking a look at some joints that have special loading conditions that will allow us to speed up that process, at least a little bit. Those joints with the special loading conditions are the ones that I am showing here on your screen. Let's get started. The first joint is this one right here on the left. Let's make the free body diagram of that joint. So that will be joint A, free body diagram. We have one load coming down, P, another load here, C, let's say another load here, B, and another load here, D. If you have a joint under these conditions, which is that they have four loads and they are collinear in pairs, like these two are collinear and these two are collinear, so we can affirm that the ones that are collinear have the same magnitude and opposite direction, meaning P equals C and D equals B. This comes from the construction of the polygon of forces that we study at the very beginning of the semester. If you remember, when we have like a particle with three forces applied, let's say we have 1, 2, 3, the graphical method to get the resultant of those three forces was to make a drawing of all the forces one after the next, one after the other. So that will be here 1 and then 2 and then 3, and the resultant of those three forces were the force that was created by joining the tail of the first force with the head of the last force. This one was the resultant. If you have a body in equilibrium, of a particle in equilibrium, the resultant has to be zero. What will be the shape of a polygon with a resultant equal to zero? That means that the last head has to meet the tail of the first force. It has to be a closed polygon. So in order for this to be zero, then we have to have, in this case, we will have to have another force here closing the polygon like that. So the resultant will be a force that goes from here to here, from the one point to the same point. In that case, the resultant is equal to zero, and we have a particle in equilibrium. So that's the case that we have here in this joint A, that we have four forces. If they are collinear by pairs, so let's make the polygons. So we have C, then we have B, then I can put P, and then we can put D. And if this is a closed polygon, is a parallelogram, and we know that in parallelogram the sides are the same length. So let's put the names. This is P, this is C, this is B, this is D. So B has to be equal to D, and P has to be equal to C. So without making any setting up of equation of equilibrium or anything, you can state that after drawing the free body diagram of joint A, you can say something like simple inspection, C equals P and D equals B. So let's say that you already know P, say this is 5 kilonewtons, and B 3 kilonewtons, or whatever, 6 kilonewtons. So then from here you can conclude that C equals also 5 and D also equals 6 kilonewtons. this is like if you have that in an example, you are calculating by the method of joints all the bars in your truss, and you bump into one joint like this one joint A here with 4 forces. It's like an X, collinear 2 by 2, collinear in pairs. Then you can state this fact without many calculation, without stating any calculation. That's the first kind of joint that will speed up your process. You spot the joint and you set up these equalities and you keep going. Let's see the next type of joint. Let me get rid of this one here. Let's talk about this case here. The free body diagram of this will be joint A, one force and another force. This is nothing new for you guys because you already saw in a previous lecture in a previous class that when a body is subjected to 2 forces, those forces have to be collinear, otherwise they have to be 0. So if they are collinear, you just set up a set of axes here. Say this is x-axis and this is the y-axis. So by summation of forces in the x direction equals to 0, you can state that D equals to B. So if you know already, say you already know that this bar carries a lot of 10 pounds, so then you know that B is equal to 10 pounds also, because this force has to be equal to this force. Very simple case, but if you spot those kind of joints in a truss, you can just write down this equation without further delay. Let's get rid of this one, go to the next one. Okay, let's go to the new case, this one here. If you have a joint where you have only 2 forces and they are not collinear, like in the previous case, if they are not collinear, they have to be 0, both of them. Why? Because if we do the construction of the parallelogram in order to get the summation of these 2 forces, if we do this construction here, this will be the resultant of D plus B. And if this is upjoint in equilibrium, that resultant has to be equal to 0. The only way that this resultant doesn't exist is that this is 0 or this is 0. If they are not 0, the only choice that we have the previous case, that both forces are collinear. Only if they are collinear, these can have certain value, so these can have the same value, and they both cancel each other, and you can have a resultant equal to 0 when the forces are not 0. But in this case that we have here, meaning two only forces that make an angle different than 180. If the angle is not 180, these both forces have to be 0. Otherwise, you see the construction, the resultant has to be different from 0 if they are not 0. So when you have one bar with 2 forces and only 2 forces, and they make an angle that is not 180, meaning not collinear, they both have to be 0 in order to have a resultant of 0 and have an equilibrium part, an equilibrium joint, a joint in equilibrium. All right, let's take a look at the next one. Now let's take a look at this one. Joint A. If we have a joint where under 3 loads, 2 of them are collinear, B and D are collinear, and there is another force that is at an angle of the first 2, the third force C forms an angle with the collinear ones. This one has to be 0 in order to have equilibrium. Why? Because if you set up a set of axes here, let's say this is X and this is Y. When you set up the summation of forces in the y direction has to be equal to 0, then you will have something like c sine of alpha, and there is no more forces with components in the y direction, right? So this is equal to 0, therefore c is equal to 0 divided by sine alpha. So c is going to be 0 in any case if alpha, if there is an angle with respect to the collinear forces. So same thing here, you don't have to do any calculations, you just set up the free body diagram of the joint, and you state just that this bar, just by simple inspection, is equal to 0. So those are the joints under special conditions. So now just let's take a look at some examples. Okay, let's make a free body diagram of this. Let's replace this support by a force here and a force here. And the rollers will be just a vertical reaction here. Say OY, KY, KX. So let's take a look at all the joints here to see if we can go quickly on some of them. For example, joint A. Joint A has two forces. There will be a force here and a force here. Those two forces are not collinear and only two forces. So in order to, if these forces are not zero, they have to be collinear. That's the only way. If they are like this, in this case, you see by summation of forces in the x direction, the horizontal force has to be 0, and forces in the y direction, so this has to be 0. Those forces have to be 0, so we can get rid of those bars. Let's continue. Joint C. Again, no, this is different case, but a special case. A joint that has two collinear bars and another at an angle. So we have that this bar has to be 0, and we can say that this bar is equal to this bar. So the one that is 0, we can get rid of that because no force here. And we can state that bar CD is equal to bar BC. The magnitude of the forces on those two bars are the same. Let's continue. Joint E. Joint E. Two forces, not collinear. They both have to be 0. So this can go away. This can go away. Continue. Joint L. Two collinear and a third one at an angle. So this bar GL has to be 0. And we can state that bar KL equals to LM. Next one, bar joint N. Again, three forces. Let's put them here. 1, 2, 3. By summation of forces in the y direction, you can see that IN has to be 0. So that bar we can remove. Well, it's not that we can remove the bar. We can remove it for our calculations. The bar has a purpose there. I will show you next to a short video where they explain why some bars, even though they are 0, they have 0 force and they are called 0 force members, they have a reason to be there. Here we can say that bar MN is equal to NO. Let's see what else we can say here. I guess that's it. You guys can pause the video and take a slow look to see if you can spot another joint that meets the condition of those special loading conditions joint. Personally don't see anything else here. This joint has five forces, so nothing to say. this one 4 forces, this one 4 forces, this one right here 3 forces, but no, we don't have collinear forces in order to say that one of them can be 0. And this one here 1, 2, 3, something 3 forces, but none of them are collinear, so nothing else we can state here. Okay, let's take a look at another example. Let's see this one. Let's make the free body diagram by removing the supports. Let's put the equivalent forces here. Fx, Fy, dy. Join A. Two forces collinear and one at an angle. One at an angle. So we have here one force and another force. So this force here has to be 0. And we can say that this force here has to be equal to the other one coming down. So this force is 1 kip and this is 0. So we can get rid of this bar. Next, join C, same case. Two forces collinear and one force at an angle. This one has to be 0. And this force has to be 1 kip, equal to this 1 kip here. So this force here, we can say that this bar doesn't hold any load. Next, join E. We didn't have this, we haven't had a case like this. Join with 4 forces collinear in pairs, like an X or an across here. So by summation of forces in the X direction, we know that EF has to be equal to ED, right? ED equals to EF. And BE equals to 2.4, so you know that this force is 2.4 because summation of forces in the Y direction has to be equal to 0. So you don't have to set up any equation, you just state that. You do your free body diagram here somewhere. When you are doing your calculations, you go joint E. You do your free body diagram, put your 2.4 here, and suppose you already know that this bar is 3. So, and this is BE, and this is EF. So you say EF equal 3, BE equal 2.4, tension. You can, if you want, you can write by simple inspection. You just write your results right there. You don't have to set up the equations or anything like that. What else? I think that's it. So know that this one is also 1 kip. This is 0, this is 0. This joint we cannot say anything because it has 1, 2, 3, 4 joints, for forces, 4 bars. Same thing here, 1, 2, 3, 4, 5 bars. Well, but with these observations, we can reduce the amount of work that we have to do to analyze the whole structure. Let's see the next one. Let's do the free body diagram of this one. So we put a vertical force here, EY, an horizontal force here, EX, and a vertical force here for the rollers, FY. And let's take a look. Special joints, B. B special joints, two forces, only two, and not collinear. They both have to be zero. This has to be zero. This has to be zero. So it's like those bars don't exist. As I say, they have a reason to be there. You will see in the next video. Another joint. Let's see any other joint that we can find in the same condition. Well, we have another special joint here, not the same, but similar, special here. We have the four forces. So this one will be four forces. So you know that this CE has to be equal to EY. So this one will go in the other direction. And EF have to be equal to EX. And you just state that and continue. What else? I guess that's it. Let's see. I don't see anything else. Well, this one has three bars, three forces. Nothing to say because nothing is collinear. This has also three forces. Nothing special. And this has 1, 2, 3, 4, 5 forces. Nothing to do. And this one, 1, 2, 3, 4 forces, but no collinear, no nothing. That will be it. Okay, let's see the next one. Let's see the free body diagram of this will be with a force vertical here and two forces here. Let's see. Joint D. Two collinear and one at an angle. So that one has to be zero. This DI has to be zero. And HD equals to AD. Joint E. IE has to be zero. Right? Because there is no force on this side to balance that one, right? That's another way to see it. And bar AE equals bar EJ. Join B. Bar BJ has to be zero. And bar AB equals to BC. Join F. Bar FK has to be zero. And bar FJ equals to bar FC. What else? Join B. Join B. Oh, we already did that. I guess that will be joint G. Bar KG equals to 0. And bar CG equals to bar GL. What else? Join L. Nothing to say. 1, 2, 3, 4 bars. No collinears, no nothing. This bar joint H, also nothing to say. No 3 bars, nothing collinear, no nothing. All right, I guess those examples show you how to use these concepts to speed up your process of analyzing a truss by the method of joints. Now let's take a look at the following video that is going to expand on these concepts to clarify any other questions that you may have and see some more examples and explain why these zero force elements there have to be there for some reasons. Okay, let's take a look.
In lecture ST13, we introduced the method of joints for analyzing determinate trusses. we learned that truss members carry tensile and compressive forces only. Interestingly, in a typical truss structure, depending on its geometry and the location of the applied load, some of the members may carry no axial force. We call them zero-force members. For example, in this truss, if the only load on the structure is located at joint C, CD becomes a zero-force member. Some trusses, such as bridges, are designed to carry moving loads. This means the bridge needs to be analyzed several times, one time for each load position. Therefore, while member AB carries an axial force when the load is acting at or near joint A, the member becomes a zero-force member when the load moves further down the bridge away from A. There is another reason for having zero-force members in trusses. A long, slender truss member subjected to a large compressive force could fail prematurely due to what is known as buckling. To prevent such a failure, additional truss members could be added to the structure in order to brace the compression member, effectively shortening its buckling length. These members often carry no significant axial force. Therefore, they are treated as zero-force members. Although we can identify the zero-force members in a truss by analyzing the entire structure, there is a shortcut for doing the same without performing any calculations. Let's demonstrate the technique using this truss. For the structure to be in the state of equilibrium, the sum of the forces acting at each joint must be zero. For example, take this joint which connects two truss members. Let's place the origin of the XY coordinate system on the joint and show the member forces. I'm going to label them P and Q. Since the equilibrium condition is independent of the orientation of the coordinate system, we can rotate the axes so that either X or Y axis becomes aligned with one of the two forces, like this, and still maintain that the sum of the forces in each direction must be zero. Note that now only one of the forces has a component along the Y-axis. P is the only force with a Y component. And since the sum of the forces in the Y direction must be zero, P must be zero. And if P is zero, given that the sum of the forces in the X direction must also be zero, we can conclude that Q must be zero too. That is, neither member carries any force. Let's simplify the truss by removing the two zero-force members. Here's another truss joint with only two forces present. Let's place the coordinate system at the joint and show the forces that are acting on it. Here, since the forces are acting along the X and Y axes already, there is no need to rotate the coordinate system. The sum of the forces in the X direction must be zero, hence Q equals zero, since it is the only force in that direction. Similarly, since P is the only force in the Y direction, hence its magnitude must be zero. Let's simplify the truss by removing these zero-force members. Now let's examine this joint. Here there are three forces. Two of them act in the X direction, and one force acts in the Y direction. Since the sum of the forces in the Y direction must be zero, Q must be zero. In the X direction, we know that the sum of P and R must be zero, but that does not mean the forces are zero. They just need to add up to zero. So the only conclusion that we can draw here is that force Q equals zero. Removing the zero-force member, we now end up with this simplified truss. Next, let's consider the top joint. Like the previous joint, here three forces are present. But regardless of the orientation of the coordinate system, the three forces result in at least two force components in either direction. Therefore, no conclusion about any member forces being zero can be drawn at this joint. The same is true if we examine this joint. Three forces are acting on the joint, resulting in at least two X and two Y components. So no zero forces can be identified at this joint either. Four forces are acting at this joint, resulting in multiple components along X and Y axes. Therefore, none of the forces can be said to be zero. As you just saw, we can identify the zero-force members in a truss using qualitative analysis. The analysis involves using a simple principle. By placing and rotating the coordinate system at a joint, If we can show that there is only one force acting in either x or y direction, that force must be zero, and the member associated with it a zero-force member. By repeatedly applying this principle to the joints of statically determinate trusses, we can identify their zero-force members qualitatively. Let's put this principle to use and see how it can help us identify the zero-force members when a couple of trusses. Consider this statically determinate truss. Suppose we wish to identify the zero-force members when the structure is subjected to a load at joint D. Keeping in mind that there is one reaction force at joint K and two reaction forces at joint A, we start by examining a truss joint that is subjected to no more than three forces. Joint C connects three members. Since there is no applied load or support reaction at the joint, it is going to be subjected to three forces only. We place the coordinate system at the joint, show the member forces, then rotate the XY axes so as to align the x-axis with the two collinear forces. Now we can see that only one force in member CE has a component along the y-axis. Since the sum of the forces in the y direction must be zero, we can conclude that CE is a zero-force member. Let's remove the member from the structure. The simplified truss reveals that there are only three forces acting at joint E. So we place the coordinate system at E, then rotate the axes like this. Now we can see that the force in member BE is the only one with a component in the y direction. Therefore, BE must be a zero-force member. Next, place the coordinate system at joint B and rotate the axes in order to show that BF is a zero-force member. Similarly, by examining joint F in the simplified truss, we can see that DF is a zero-force member. The members on the right side of the truss can be examined in a similar manner. From joint I, we can conclude that HI is a zero-force member. At joint H, we can show that HJ is a zero-force member. Also, JG is a zero-force member. And we can easily show that GD is a zero-force member. No further simplifications can be made past this point. The simplified truss can be analyzed in order to determine the support reactions and the remaining member forces. Let's consider another example. This truss is subjected to two concentrated loads, and given that the structure rests on two pin supports, there are four support reactions. We scan the truss joints with two or three forces only. Joint B is a good candidate. If we place the coordinate system at the joint and draw the member forces, we can see that the force in member BD is the only one acting in the x direction. Therefore, BD is a zero-force member. Let's remove it from the structure. Next, consider joint E. Since the sum of the forces in the y direction must be zero, DE must be a zero-force member. Furthermore, upon examining joint D, we can conclude that CD is a zero-force member. Why? Because after aligning the x-axis along line AF, we can see that CD is the only force with a y component. And since the sum of the forces in the y direction must be zero, CD must be a zero-force member. Finally, if we place the coordinate system at joint C, since there is only one force acting in either x or y direction, we can conclude that both AC and CF are zero-force members. Now let's examine the remaining joints. At joint A, there are two reaction forces and one member force. Regardless of the orientation of the coordinate system, these result in two forces along the x-axis and two forces along the y-axis, so neither force can be said to be zero. At joint F, the three existing forces yield two x components and two y components. Therefore, neither force can be said to be zero. Joint H is subjected to 4 forces, 2 forces in the x direction and 2 forces in the y direction. Therefore, neither of the member forces can be said to be zero. At K, although there are only 3 forces present, they yield 2 x components and 2 y components. Therefore, neither member can be said to be carrying a zero force. Joint J is similar to joint H. There are 4 forces present, hence no member can be said to be carrying a zero force. Joint G is subject to 5 forces. Obviously, none of the members can be said to be carrying a zero force. Finally, at joint I, the existing 4 forces create multiple force components along both axes. Therefore, neither of the 2 member forces or the support reactions can be said to be zero. Now it's your turn. Identify the zero force members in the following trusses.